optimize the inventory levels and improving the logistic efficiency. And also the energy management when come to the power. See here also we can monitor the energy consumption patterns, and we can identify the inefficiencies. Suppose if there is a mission is running but there is no requirement of the mission, and we can identify and we can stop it, and we can reduce the cost, and we can decrease the electricity bill and all the things. And when you come to the worker safety, when you are going to the internet of things, when you are going to wearable the IoT device and the environmental sensor can monitor hazardous conditions, and worker health matrices like triggering instant alerts, and he can ensure a safe or working environment. When the human being can wear this wearable IoT devices, if anything emergencies happen in the industrial environment, he can get the information and can try to escape from the hazardous problems, or it may be like a dangerous problem. Like when come to the second thing is that the industry 4.0, we are going to involve in the automation and robotics. See, automation means we all know that we are going to using machines to perform the task automatically without needing of any human being else. Then when you come to see these robotics, 1 minute, sorry. Yeah, when you are going to add the robotics, robot will be added as a powerful, and we are going to use precise robots that can do repetitive, difficult, or dangerous work. It can do. Generally, in industries, we are going to use as I told in the second slide itself, robot can do the repetitive tasks and whatever the difficult tasks, and it can do the dangerous work. It can be capable to. And also, when we are going to introduce these robots, it can reduce mistakes. Like as a human being, we can do the lot of mistakes, and it will save the time and protect workers from the risky jobs. And these robots can work faster and more accurately than human being, and in many tasks. Suppose when the example you can see the robot arm, when we are going to do the pick and place operation, like if we are going to pick and place products from one place to the another place, or and continuously it can do without stopping from how much time you require, without there is no rest is required. Like when you come to the third integration of the smart manufacturing is big data and analytics. Here what will happen, whatever the factories we are using, it produce huge amount of data it is producing. Why? Because we are providing everywhere there is a sensor, each machine is providing lot of data. For every second we'll get lot of data. And here what will happen, whatever the data we are getting, the data, it may be reading of the mission, it may be product counts, it may be temperature, or it may be more. Here what will happen, the big data will collect all the information and do analyzation and find the problems. The big data, what it will do, whatever the data is coming from the sensor, that sensor data it can be collected, and it can do analysis, and it can find the problems, what are the problems are coming in future, and what that can be predicted, and it can be improve the operations. And also this can be helpful to the big data can be helpful to the factories make smart decisions instead of guessing. Generally what will happen, sometimes people without sensor data we will guess, okay, maybe this bearing may be fault, or this maybe this mission may screw may go out, like that people may think it is that this without unnecessary guessing we can get the correct information, and we can take the correct decisions within the right time we can do it. Like when you come to the example, you can see by studying the data, this big data, what will happen, it can discover that one mission always slows down at night, and then the technician can fix the issue and improve the productivity immediately. Like when it comes to the artificial intelligence, we all know about artificial intelligence means the robot, or it may be a mission, or it may be a system. When you are going to provide a AI capability, the AI will think the whatever the machine, or it may be a robot, it can also think like as a human being. Why? Because as a human being we are an intelligent. Okay, we have already own intelligence, we can behave like an intelligent person. In the similar way we are going to expecting the missions, and your robots can behave like an intelligent. Here what will happen, this AI will allow the missions and computers can think how human beings in thinking, and it can make the decisions. Okay, after thinking we can make the decision based on the data. what the data received from the sensor based on the previous data it can think. And also it can predict it, and the machine might break and suggest better settings and detect defects and product increase the product quality and increase the productivity automatically. And also this whatever the artificial intelligence we are going to use in the smart manufacturing, the artificial intelligence it can reduces human workload and it can be helps the factories run more intelligently. See, when we are going to use this AI analyze the vibration data, and once the motor will fail in 2 days, generally what will happen due to the suppose, see, after running your mission, due to maybe your motor shaft may be fail or it may be motor may damage, and all these things based on the data it can be analyzed and it can be tell, and it can be suggest to the technician immediately it is going to maintenance is required the particular type of motor and all, otherwise it can be break, that before it breaks you can do the maintenance. Like you can see the cyber physical system. See, cyber physical system, generally what will happen when we are going to introduce this cyber physical system in smart manufacturing, here the missions and digital systems are connected and work together like a single unit. Like your mission will be there, your digital system will be there, all together, and like it can work as a single unit. And you can see the sensors collect the data about by using a physical mission, and the computer process the data and then sends the command back to the mission to adjust its behavior. Like, see, like how the when we are doing some mistakes as a human being and someone is corrected, immediately we are going to correct it in the similar manner. Whatever the data collected from the mission, that data we are going to send to the computer will process the data, and the computer will send the feedback. According to the feedback the machine can adjust its behavior. You can see the mission speed, or if you suppose you can think it of, if it is detects a small error and it automatically corrects that small error by using the computer feedback, it can be corrected and without any human help. And the next one it will come to the cloud computing. You can see in the cloud computing we are going to store the data, whatever the data we are going to get it, and that data, the fact complete data we are going to store there. See here what will happen, we are going to storing and we are going to processing the complete data received from the factory, and that data we are going to utilize whenever it is required. And this data maybe allows managers to access the information from anywhere. Suppose if the technician or if maybe some person, suppose most of the time what will happen, we may have seen in our industries many manufacturing machines or many systems or robots or we are importing from other countries, and maybe the mission maybe we are import from other countries, the person those who are going to repair the person may be in the somewhere and our mission is in somewhere. But the person can get the data, the whatever the data is sensor data or camera data, he'll get it, and the data we have stored in the cloud computing, he can access the data and he can give the information what type of problem is coming and when it is going to reduce it and how to reduce it, everything he is going to inform to the nearby the technician. And also it gives factories more computing power without buying expensive any hardware, and it will helps to analyzing the large amount of data quickly. And you can see the example, you can see suppose if the manager checks real-time production data, how much production data will be there from his abroad or from his home, and he can connect with cloud and he can operate with laptop with the cloud and he can see. Like you can see the last one is called digital twins. Generally when come to the digital twins, what we are going to see, we are going to virtual model, we are going to create the virtual model before going to the real model. And here also we are going to make the virtual model of real mission, and we can see the production line and we are going to see the entire factory by using the digital twin, and we are going to be make it the running that the entire factory, and we can see the how the real system, if you want to before going to move before going to operate the real system, and we can see in the digital twin and how it behaves, it just like a real system it is behaving, or because it may receive the live data from it. And generally, what will happen? Engineers, what they will do? They will use the digital twins to exchange text changes, and they are going to use the fixed problems, and they are going to improve the process without stopping in the real mission. Why? Because parallelly they are going to do testing on the digital twins, and they can understand and they can see what type of problems are coming. That problem they are going to fix it, and they are going to improve the productivity. And you can see, suppose if you are going to increase the speed of the conveyor belt, engineers test the digital train to make sure won't be cause any damage of the conveyor belt. Then only they can increase the speed of the conveyor belt. Otherwise, it may be damaged. They cannot do it. So when we come to the smart manufacturing, today's we are discussing about smart manufacturing. I told you in the smart manufacturing we are going to integrate with all these things like intelligence, AI, and Internet of Things, data analytics like cloud computing, big data, like you can see cyber physical systems. And see here what will happen when we are going to make combining all these things and your system, whatever the manufacturing you are doing, that should be a smart manufacturing, and it can be create a highly efficient, flexible, and intelligent production system. Why the people they call it as a smart? Because the reason is that we are going to use lot of intelligent technologies like IoT, cyber physical system, cloud computing, big data, AI, and all these technologies that allow the missions, systems, and the process to think, to learn, and to communicate, and to make the decision just like a smart person does, how he can take the decision accordingly. These missions can take it. When we are going to make your mission like smart and it can be capable to take the decision, then your complete system or complete industry, it should be a smart. The benefits, what are the benefits we can get by when we are going to use the smart manufacturing? We can increase the efficiency, see, and we can increase the greater agility and resilience, and we can improve the decision making, we can improve the enhanced innovation, we can improve the worker safety. When you come to the increased efficiency, we can see when we are going to use the smart manufacturing by using all these technologies, when we are going to integrate it, we are going to do the automation, automate tasks, and we are going to reduce the waste, and we are going to improve the forecast accuracy to lower cost only we can do it. And when you are going to show the greater agility and resilience, and we are going to allow the business to quick adapt to change in demand. See, we are going to suppose if any problem will be there, according to the situation, we can quickly change your business model, and we can adapt to the changes. And according to the demand, we can make it and the scale production up and down, whatever the suppose if more output is required, we can increase the productivity, and if it is less demand is there, we can decrease also. And we can improve the decision making. Suppose if there is a problem come, what type of decision we can, and by using this deep learning or machine learning, the real time insights we are going to use like when we are going to manufacturers to make more informed and timely decision. And the next one is the enhanced invention. We are going to create opportunity for new business models and personalized products and better consumer customer experience and improved worker safety. Why? Because the main thing is that when we are going to make your system should be smart, your industry should be smart, your manufacturing system should be smart, and not only to predicting the your mission life, not only predicting the your robot life, or you are going to increase the productivity, we are going to better productivity, and we are also looking about the worker safety. And by using all these type of technologies, we can reduce the burden or mundane task, or that means the difficult tasks, allowing the human workers to focus on more complex jobs and improving overall safety through data driven technologies. Like you can see in this picture, how the smart factory will be there. You can see in the smart factory there are many machines are there, and machines with robots are communicating, and a robot can work earlier there is a human being in the place of robot. Now they are removed the human being, and whatever the task is going to done by human being, the same task robot can be capable to do it. You can see here, see when we are going to do the convergence of the virtual and physical world, when we are going to do the smart factory, we are going to integrate, as I told you in the previous slides, like we are going to integrate AI, machine learning, automation, and all the things we are going to. See, when we are integrating all these things from entering the raw material into the industry and getting the complete product out, at the same time, we can see the status of each and every mission, that all the information we can get it, then only your complete industry should be smart. Like you can see the shaping the factory of the future. You can see the factory today how it is look like that, and in the future how it is look like that. Today you can see the shop, the how the factory will be there. In the future we are going to use, when you are going to use like industry 4.0, by using like your big data, like your robotics, like your cyber physical system, and we can predict all the problems, each mission whatever the problems are coming, and we can check the quality of the product before go entering to the market, and we can integrate one system with another system, and we can use our mission vision system, and we can predict the failures of the mission. All these things we can and at the same time human can also variable like IoT related devices in the when they are moving inside the environment in the industry, then the human can understand if any problem will rise, if any danger problem or situation will be arise in the industry, he can save. Like I told you, when the robots in smart factories, what will happen? Human can work with the robots, or human collaborating with the robot. Why? Because in the for a safe workspace, what will happen? Earlier, people are using like industrial robots. For industrial robot, human cannot enter when the robot is working. But when it come to the collaborative robot, human can sit with the robot according to his customization. When this technology it was came into the industry 4 5.0, according to the customization, whatever the customization we want to do, we can do it. The human can sit with, human can work with the robot. And you can see here the robots are safe for humans, and it can create space required for the traditional robots. You can see the pictures, the human is working along with the robot, and according to the whatever the requirement, customer requirement, and the human can customize the product, and he can deliver the product as per in time only. Like here I'm going to play I'm going to play a small video. See how the smart factory will be there, how the industry in the industry, how the robots are involved, how it became like a smart factory. You can see a small video. 1 minute. 1 minute. Yeah, like this is the one of the automobile industry. You can see. Hello. మన క్లాస్లో ఉన్నాను. ఆన్లైన్ క్లాస్.
FANUC robots and factory automation solutions have been facilitating industrial production for over 60 years. FANUC is present in 120 countries, including Hungary, assisting key sectors like the automotive industry, for example, at the Audi Hungary Motor Limited factory in Zsur, where they are developing and manufacturing cars for the Audi AG and the Volkswagen Group. Audi Hungary is one of the companies with the largest turnover and export in Hungary, producing 2 million engines and 135,000 cars in 2014.
Like you can see how the robots are doing the particular operation, like when they're going to do the like welding operation, like or finishing operation, like bending operation, how the robots is doing very systematic manner, and how the quality of the product should be there. Sorry.
Robots to reach our targets, using 2 million engines and 135,000 cars in 2014. In our experience, FANUC robots work reliably at our factory. We are constantly improving our production and install robots to reach our targets. In environments where we need to work with high pressure or temperature, the robots are up to the task and deliver quality standards, which would not be possible with human machining. Essentially, robots are used for applications too difficult for humans, or where rapid machining is required. Our colleagues like working together with robots as they make human work easier by delivering these
Like you
tasks.
can see, the
It's
robots
very
are
important to program
by
these
using that
robots correctly.
computer
And when
vision.
problems
Like
arise,
robots,
it's usually not the
the
robot that
inspection is
causes
going
them,
on.
but improper programming or the lack of maintenance. Regarding this, I'd like to highlight that FANUC robots are easy to program, dependable, and we have a very good experience with them.
Yeah. The next, when you come to the types of robots, you can see generally robots we are going to categorize it two types. Generally, people may call it as industrial manipulators or industrial robots. The other type we are going to call it as a mobile robots. You can see here the one is called industrial type of robot or industrial manipulator. And there are again two types in industrial robots. Like one is the serial manipulators and another one is the parallel manipulator. 1 minute. Sorry, 1 minute. When you come to the serial manipulator, you can see all the serial type of manipulator we are going to use in most of the industries to do the some particular type of task. Like it may be do the pick and place operation, or it may be do the like welding operation. Like we can do the painting operation, we can do it. And only as I told earlier, also only we have to change in the end effector. But the other type is called this. You can see the previous manipulator. You can see all the links are connected in serial manipulator, connected in serially. But when you come to the parallel manipulator, you can see here the links are connected parallelly, and one link is connected parallel with the other link, and there is another link, and all the links are connected parallel. And see here there is two platforms are available. One, it is the base platform, and second one is the working platform. The top platform we'll call it as a working platform. And if we want to do the any like us, see the advantage is that by using this parallel manipulator, you can work, you can tilt your platform, or you can work, you can tilt your workpiece. If you are going to place your workpiece on top of the parallel manipulator, we can tilt it like both in linear moment in x direction, y direction, and z direction. At the same time, we can rotate along the around the x-axis, around the y-axis, and around the z-axis. Also, we can do. And also, there are many mechanical applications or in other applications we can use this platform. Like if you want to track the radar signal, if you want to track the solar sun tracking, we can do it. And also nowadays people they are going to use in mechanical application like metal forming. Like people they are going to provide the tool whatever the metal forming tool they are going to provide on the above platform, and they can do by using this parallel manipulator, they can make like sheet metal forming, they can do it. And there is a other type, we will call it as a mobile robots. And in the mobile robots they are categorized into two types. One is the wheeled robots and second one is the legged robots. See, these wheeled robots, it can be capable to move in the if the surface should be in the flat, and the legged robots, it can be capable to move if the surface cannot be flat, and it is an unstructured environment also, it can be capable to move. Why I am going to discuss about this mobile robot? Suppose if you want to move your industrial manipulator, the entire environment, you can make your industrial manipulator on top of this wheeled robot, or it may be on top of this legged robot. We can make it, and we can move your entire environment of the industry, and we can do the task, whatever the task we perform in your robot, we can perform it. Like you can see, and there is a category, we will call it as a, these robots will call it as a stationary robots. Suppose why? Because these robots will be one place, and these robots will call it as a mobile robots. Like you can come to the stationary robots, you can see like generally the robots we are going to classify like based on the coordinate system. Like generally whenever we are going to develop, we are going to classify the robots based on coordinate system. The coordinate system, we are going to see like what type of coordinate, whether we are going to use prismatic joint or whether we are going to use the revolute joint. See here what will happen based on the classification, the robot classification. When we are going to do the based on the coordinate system, we can see the first categorization we will do the Cartesian configuration. Here you can see we have considered only the 3 degrees of freedom for each robot. You can see here the Cartesian configuration, all the joints are moving in the linear moment, and all the joints like in along the x-axis, along the y-axis, and along the z-axis, and your manipulator is moving, and all moments are 3 moments are in linear moment, or we'll call it as a prismatic moment. That's why it should be a PPP mode. It is a prismatic moment, and whatever the work volume it can generate it, that it is a cuboidal work volume it can generate it. And when you come to the cylindrical robot, and here what will happen, there are two joints will be prismatic joints and one should be a revolute, and it will generate the workspace or work volume it can generate, like cylindrical workspace it can generate. When you come to the spherical robot, the other classification, here what will happen, whatever the workspace it is going to generate, it is a spherical type of workspace. And here what will happen, one is prismatic and two should be revolute joints. And there is the other type, the fourth category, we are going to make it as the industrial robotic arm or industrial manipulator, that is called articulated configuration. See, when we have considered all 3 degrees of freedom, here all are revolute joints. Most of the cases, what will happen, most of the industrial robot, it consists of all 3 degrees of freedom will be there. And you can see the whatever the articulated robot, the configuration or the visibility, when you can see this article robot, it look like a human arm. How, as I told earlier, in the human arm also we have a shoulder joint, we have elbow joint, we have wrist joint is there. The next we are going to call it as a the SCARA robot. It is a special type of robot. The full name we will call it as a selective compliance assembly robotic arm. We are going to use this special type of robot for assembling purpose. Like you can see, like if you want to assemble like your chip board or motherboard, if you want to make your circuit and all the things, the resistor and capacitor, and we can use this type of robot. The robot can take care and it can be very precision manner. It can be do it. Like there is a other type, as I told you earlier, like human nowadays in industry 4.0, human is collaborating with the robot, and human can customize whatever the work he want to do it. That is called collaborative robot. The difference between industrial robot and collaborative robot, industrial robot, human cannot sit and he cannot customize it and he cannot do the work with the industrial robot. But collaborative robot, human can do it. He can operate the by his hand. But the another difference is called industrial robot. The weight should be more. It may be tons, but when you come to the collaborative robot, the weight should be in kgs. It may come like 50 kg or 40 kg. The last type is called parallel type of robot. I already discussed in the previous slide. See, when you come to the end effector, generally what will happen, every robot, we are going to make it as an end effector. The end effector generally where we are going to attach, as I told previously also, we are going to provide the end effector in the wrist position. And why we are going to provide the wrist position, we are going to perform that specified task, we are going to accomplish the task by using, like it may be in the end effectors, we are going to categorize two types. One is the gripper, second one is the tools. The gripper, as I told previously, in the similar way you can see, it will be grasp the objects for pick and place operation. The tools we are going to do the some specific task, like it may be a spray painting or it may be welding. Like you can see in this picture, there are different types of grippers are there. You can see when you come to the grippers, there is a electronic gripper or maybe mechanical grippers will be there. Like you can see vacuum gripper, like electromagnetic gripper. There are many varieties of grippers is there. It is available in the market. That depends upon the task what we want to do. Like when you come to the tools, you can see like you want to do the welding operation, you want to do the cutting operation, you want to do the painting operation. That depends upon the particular operation. We can change your end effector. Then effector it is we can attach it in the wrist position. The next we are we are going to use the robots in industry. Most of the time, what will happen? The robot can work in the industry. The robot should be there and missions should be there. But how the robots are arranging in the industry? That generally we will call it as robot cell layout. The robot cell layout is the complete system. We are going to include the robot controller and other peripherals. Like you can see, like when we are going to use like a part positioning and safety environment. Like you can see, these robot cells are sometimes we are going to call it as a work cells, and we are going to organize various arrangements like layouts. Generally, what will happen? We are going to classify. There are three ways we are classified. One is robot centered cell and inline robot work cell like mobile. When you come to the robot centered work cell, here what will happen? The robot is there in the center, and all the machines are surrounding of the robot. Like you can see in this picture, easily you can understand this is the robot is center, and there are whatever the missions we are going to do to make the raw material into the final product. All the missions are be spacing. All the missions are placing at the surrounding of the robot. What robot will do? Whatever the pick and place operation, each mission you want to put the raw material, or it may be finished product if you want to put it, that instead of human being, this robot can take care, and without human being we can do the task in a smart environment. Like when you see, the other type is called inline robotic work cell. Here what will happen? In the previous case, robot is center and missions are in the surrounding, and that means surrounding of the robot. But in this case, what will happen? The robots are staying, and the whatever the raw material is there, raw material is moving on the conveyor belt, and for it depends upon the task robot need to do. That depends upon the task. The raw material can stay in front of the robot. How much time it is required, it can be stay. Like you can see, the other type is called mobile work cell. Here what will happen? Like raw material is entered, like when it is coming from mission 1 to mission 2, then it will go to out. Like before, while moving like this, the robot will also move by using like railing moment, and it can collect the raw material from the conveyor belt, and it will keep into the mission 1, then go to mission 2, then it will go to the mission like output, where the final finishing product we are going to put the output of the conveyor belt we are going to place it. This is the way the people they are going to operate. Like it may be a robotic centered cell, or it may be inline robotic cell, or it may be a mobile robotic cell. We can do it. Like you can see, there are few mechanical applications we can use these industrial robots, like material handling, like loading unloading application. Suppose when you see the like from one place to another place, if you want to move the robots like your material, like you can see Amazon warehouse, like Flipkart warehouse. Like see, as I told earlier, this there is it is a mobile robot. On top of the mobile robot, your manipulator is there, and this mobile platform can move from entire the environment, and the manipulator can do the particular task. It can take the boxes, and it can place it in the racks properly. And that means it is what it will do. It is doing the loading and unloading, and also it can do the material handling. These are the different types of applications the robots can use in industry. And like you can see, the other you can do like some die casting application, like plastic molding, like machining operations, like forging operations, like press working. The benefits we can get it when we are going to use the robots, we can get the precision of the product, and we can increase the accuracy, and we can increase the safety, we can increase the speed, reliability, flexibility. All these things we can increase it. And also we can use the dangerous work environment. We can also loading unloading we can do, and we can avoid this dangerous work environment. And when you come to the assembly, like you can see the industry how the depends the fitting of the vehicle, or it may be fit manufacturing of the product, like assembling purpose, like creating, like if you want to manufacturing of any product, complete product, we can manufacture it, and we can fix it by using this tool. We are going to use the assembly tool. Like inspection application, when you go for industry, the raw material is converted into finished product. When it is the product was finished, when we are going to leave the product in the market, what will happen? Whether the product have any pits, whether product have any cracks. Why? Because we have to do the quality testing before going to do the quality testing. For under the quality testing purpose, we are going to attach the camera for the robot, and robot will be standing the beside of the conveyor belt. It will capture the each finished product, and then it can be analyzed. It can be it can be analyzed by using like your AI or machine learning algorithms. Then we can see whether it is any defective, and we can throw out if there is no defective, and the finished product can send directly to the out market. Like robots we can use like welding application, as I told in the previous also. Like robots we can use the spray painting application. Like the another advantage is that robots people they are going to use like a 3D printing, like additive manufacturing application. Like we all know that we have seen like nowadays the 3D printing technology is growing like anything in the market. These serial type of robots they are going to use the 3D printing. And recently, I have seen one video. I think nowadays the civil engineering people they are going to use these type of robots for constructing the building. That means 3D printing means or additive manufacturing means we are going to do the layer by layer deposition. The civil engineering people what they are going to do, they are going to do by their concrete mixture layer by layer deposition, and they made the walls and they are fixing the walls for houses. Like the other application, this setup was made by our triple ITDM Karnool in the mechanical department. This is one of the collaborative robot, and we have purchased and we have taken like the welding setup, and we are going to use this setup like MIG welding. At the same time, we are going to use the like layer by layer deposition, like wire arc additive manufacturing. We are using the wire, and we are going to do the layer by layer deposition by using this collaborative robotica, and we are going to test it. What are the mechanical properties will be there? All these things we are going to test it. This is the we are going to do the here we are doing like layer by layer deposition in our laboratory by using the collaborative robot. And you can see these are the specimens we made. You can see in the top right corner. Like I think there is a time I'll show you what generally we are doing in triple IDDM Karnool. Basically, I worked in my PhD in robotics in the bipod robotics. 1 minute, 1 minute. I'm going to close next 5 minutes. Please wait. What we are doing in our institute, see, we are going to develop like different types of mechanisms of the robot, and we want to take these mechanisms like in a little bit high level, like intelligent type. And this is the one of the mechanism of students was developed like snake type of robot. You can see how the snake is behaving. This is the work we are doing at triple IT, and this is the one of the simulate platform at our institute, like what flapping wings flight simulator. And this is the earthworm robot, and you can see this is the like unmanned aerial vehicle. Like this is the two-wheel robot. Like we are going to try to balance up the robot. And this is the one work we are doing like climbing mechanism for trees. And this is the project funded by DST, and we have developed a climbing mechanism for cutting the coconut tree. And this is the bipod robot, like two-legged bipod. See here, what we are going to do, we are going to develop the control algorithm when the robot is walking on the different types of terrains, and how the robot is balancing. That we are going to test it here. And this is the actually in this case we have developed 18 degrees of freedom, but this is the work done by one of my first PhD student. He has developed a 16 degrees of freedom humanoid robot, and he has awarded his degree, and at present he is in postdoctoral fellow in Manchester University. Like his case he's chosen like ditch and obstacle crossing. Like in triple ITDM kernel, one of my PhD student, we are going to develop the control algorithm, and we are going to make the computer vision for like a quadruped robot, like four-legged robot. This one of our students is developed in our laboratory in triple ITDM kernel. See, our aim is that we are going to mimic the like biological things like human, and we are going to mimic the like quadruped robot. and these are the publications related to my work. And coming to our institute, I will give 1 minute. Our institute was started in 2014, and the number of faculties we are working around 50 members. And we have programs BTech in mechanical engineering, BTech in electronics engineering, BTech in computer science and artificial intelligence and data science. And in mechanical, we have the specialization, robotics and automation, and we are offering PhD program also. And if anyone interested to do PhD or to join MTech, they can approach through my email ID. And our admissions MTech program, BTech in JEE Mains and MTech, there are two ways we can join. One by using GATE, and second in we are going to release the notice for those who are not qualified in the GATE also, like payment based they can join. And PhD program, we are offering the stipend like 37,400 per month. Also we are also offering internship program for various college students, like offline or online mode, like winter and summer internships. If any student of yours interested to work in the field of robotics, please send their resumes to my email ID. And I'm stopping from up to here my talk, and this is my email ID. If anyone have any queries, they can contact, and this is my mobile number. Thank you. If you have any doubt, now we can discuss. Now the session is open to you people. Please try to interact with if you have any doubts. Okay, Dr. Vamsi Krishna and Dr. Guru Mahesh.
Sir,
Thank you, sir.
Yeah, thank you.
1 minute also, sir. Dear
Yeah.
participants, any doubts? Can you rise in, unmute yourself and raise the doubts? Any questions?
Yeah, I'm seeing your chat also.
Thank you, sir. Nice session.
Thank you, thank you, thank you.
Participants, any doubts?
Sir, it was a very nice session. I wanted to ask, sir, in controlling this kind of robots, you use conventional control methods on state space based, or you use intelligent like soft
No,
computing, or
yeah, we are using like soft computing based controllers, like neural network we are using.
okay. And what about, sir, reinforcement learning? Because see, I am having expertise in modern or traditional control system, but now it has gone very far, very beyond. So it is
Yes, yes.
necessary to adopt or learn reinforcement learning, sir.
Yes, we can develop, but anyway, whenever we are going to do this reinforcement learning, like soft computing based learning, but before entering to these controllers, we have to work in like your.
Hello, sir.
Yeah, please. 1 minute, 1 minute. Is it audible? My voice?
Yes, sir. Audible, sir.
Yeah. We have to first understand the normal controls like nonlinear control, linear controllers. We need to understand. Then we have to jump it there.
Okay, sir. Thank you, sir.
Thank you.
Sir, in robotics, what is meant is singularity, sir? Singularity problem.
Singularity.
Yeah.
Singularity condition, when we will get it, generally what will happen when the robot is going to, there are two ways, two singularities we can possible. Like when your arm is completely stretched, like completely open, like 180 degrees completely. Okay. And the second way, when we are going to completely close, like near to the your base point. Hello.
Okay, sir. Thank you. That means it gets arrested in those two positions.
Yes.
It's locked.
Yeah, that means we will last 1 degrees of freedom there. Okay. See, when it is completely stretched, if I open completely my arm, but now I'm moving based on only my shoulder movement only, but there is no help of my elbow movement. That means we are losing 1 degree of freedom.
Okay, sir. Thank you, sir.
Thank you.
Sir,
Yeah,
Mahesh
please,
sir.
please.
Sir,
Yeah, please. Sir, please.
Tell me, Vamsi sir.
Sir. Sir, Mahesh sir.
Sir, your voice is audible, sir. Tell me, sir.
Yeah. Can I go for the closing remarks?
Yes, sir. With permission of Sir Ravi, sir. Sir,
Yes,
shall we
yes.
close the? Sir?
Yes, yes. Yeah.
Thank you, sir. Thank you. Good evening once again, respected faculty members, dear colleagues, and all participants who joined us today. We have come to the end of this highly insightful session. Focus topic: integration of IoT and robotics in smart manufacturing. And heartfelt thanks to our resource person, Dr. Ravikumar Mandava, Assistant Professor, Grade 1, Department of Mechanical Engineering, IIT DM, Kurnool, for delivering such a wonderful, practical, and future-oriented session. And sir has given clear explanation, real-world examples, and seamless way connected to the IoT ecosystem and robotic applications in smart factories have truly enriched all of us. We are extremely grateful for the time and expertise you so generously shared with the teaching and learning community. We hope the knowledge and insights gained today will help all of us integrate IoT-driven robotics more effectively into our curriculum, research, and industry collaborations, thereby preparing our students for the factories of tomorrow. Thank you once again, Dr. Ravikumar Mandava Garu, for
Yeah, thank
coordinating
you.
with us and
Thank
given
you,
a
thank you.
clear explanation. Thank you, everyone.
Thank you. Can I leave?
Wishing you all a productive and safe evening day ahead. Thank you. Thank you, sir. Thank you for giving a valuable information and at your hectic schedule. Thank you, sir.
Hello. Hello.
Sir, please.
Sir.
sir, I think sir has left, sir.
Sir, Ravi sir has left, sir.
Yes, yes.
Sir, Krishna, sir. Sir, Krishna, sir.
Maybe sir has not yet joined, sir. We will take 3 minutes or 5 minutes break, sir.
We will take 5 minutes break, sir.
Okay, sir.
Hi, good evening. I joined with the other link, so I was waiting.
Sir, Krishna, sir.
Yeah. Good
Sir,
afternoon.
voice is audible, sir.
Good evening, Dr. Guru. Hello. It's audible. I'm not sure whether you are able to hear me.
Good evening, sir. Good evening, sir. Audible,
Are you
sir.
able to hear me? Yeah.
Yes, sir. Yes, sir. We can hear you. Yes, sir.
Yeah. Okay. I think maybe Dr. Guru is not able to hear me.
Sir, with your permission, we'll start the session within 2 minutes, sir. We have given break, sir.
No problem. No problem.
Thank you very much, sir. Thank you.
Sir, good evening, sir. Krishnaya, sir. This is
Good
Guru
evening,
Mahesh.
Andy. Yeah, good evening, Andy. I think you were not able to hear earlier.
Yes, sir. Bluetooth is connected to mobile, sir.
Yeah. That is sometime doesn't work actually. That is the problem. Yeah. So
We will make 4 to 2 minutes, sir. Participants will given the best to now break.
So it started 6 o'clock, is it?
Yes, sir. Yes, sir. Ravi sir just now can finish the class.
Okay. So then means up to 9 o'clock they have to be there. 6 to 9.
Yes, sir. Yes, sir. Yes, sir.
So is it effective compared to the previous one?
Sir.
Is it effectively? I mean, participants and all that effectively there.
Yes, sir. Yes, sir. Up to last, they will have 250 plus participants in Google Meet, sir.
Okay. So
And
this
we
is
do
so many joined. 250 or
yes, sir. Yes, sir.
223. Okay.
Yes, sir.
So
30
these are
to
all
40
from
members, they're watching live.
Pardon?
We are giving YouTube live also, sir.
YouTube live also. Oh, okay. That's nice.
Here, there are 30 to 40 members, they're watching continuously. Yesterday, I seen the analytics.
So where is the YouTube link? Can you share?
I will share to you, sir.
Yeah. So you have a recording facility also on this, seems to be, right?
Yes, sir. Yes, sir. We have recording facility in Meet.
Okay.
And I use OBS for live, sir.
Okay.
Screen recording.
I have cold and cough.
Yes, sir. Yes, sir. I'm watching, sir.
I thought I'll request to change, but I'm not sure whether I'll be recovered. So I thought, okay, let me complete.
Okay.
Sir, let's start, sir. Guru Mahesh, sir.
Sir, we'll...
Krishna, sir, with your permission, let's start, sir.
Sure.
Yes. Sir, Vamsi, sir, please, sir.
1 second, sir. 1 second. I'll start. Come back. Sir.
Okay, sir.
Okay,
Sir,
sir.
sir. Slide change, sir.
Yeah, this is
This is our presentation, sir. We are changing your proposal.
okay. This is yours. Okay.
Sir, after your invitation, we will share you, sir. You can share.
Fine. Okay.
Right, sir.
Good evening, participants. Hope everyone will join back, resume to seats. So Krishna sir is available to give the next lecture. So first of all, I would like to thank you, sir, for that team who has given me an opportunity to introduce today's speaker. Thank you, everyone. A very warm welcome. Yet another power pack session in our AICTE ATAL online faculty development program on robotics for Industry 4.0, enabling smart manufacturing. Today's topic is extremely relevant and futuristic. Role of AI and cyber physical systems in robotics. It is my proud privilege and absolute pleasure to introduce today's distinguished resource person, Dr. J. Krishnaya, Associate Professor, Department of Mechanical Engineering, Indian Institute of Information Technology, Design and Manufacturing, that is IIITDM, Kurnool. Sir is an outstanding academician and researcher with a PhD from the prestigious IIT Kharagpur. He brings with him a remarkable track record. 13 granted utility patents, 3 design patents, 4 copyrights, more than 15 reputed journal publications, and 25 plus international conference papers. Authored, contributed to 3 books, reports, chapters. Successfully completed consultancy projects worth 3.5 crore over 15 years in the domains of artificial intelligence and neural networks applied to mechanical systems and manufacturing. And he is a principal investigator for project worth 91.11 crores sanctioned by premier agencies such as DST, DRDO, MEITY, and Ministry of Education. Currently, Dr. Krishnaya is actively working on applied research in data-driven systems, predictive modeling, controlling, and optimization, areas that are the very backbone of modern cyber physical systems and Industry 4.0. With such vast experience in both academia and high impact funded research, Sir is undoubtedly one of the most sought after experts when it comes to the convergence of AI, robotics, and smart manufacturing. Let us please put our hands together and accord a warm and resounding welcome to Dr. J. Krishnaya sir as he takes us through this enlightening session on the role of AI and cyber physical systems in robotics. Welcome on board, sir. Thank you, sir. Thank you very much, sir. Kindly accept our invitation, sir. Sir, your voice is not coming.
You are
sir.
on mute, sir. You are
Please
on
check
mute.
your voice.
Yeah, thank you very much, Vamsi, for introducing me. But now there is a lot of load on me. So because you have put so many strong words, which I am not sure whether I can cope up with, but let me try it. So are you able to see my screen?
Yes, sir. Visible
Yes,
and
sir.
you're audible. Yes.
Okay. So, yeah, as part of this robotics for industry 4.0, enabling smart manufacturing. So here, I think for last 4 days, you would have gone through maybe till now 7 talks, and this is the 8th talk. So you would have understood by now the importance of maybe the robotics in the industry 4.0 environment. Of course, smart manufacturing is a part of industry 4.0 only. So if you see that, I mean, maybe how the progress of robotics has happened over period, and then how these technologies like AI has become the forefront in many areas, including manufacturing, which is relevant for the uh, industrial environment or industrial basically uh, industrial revolutions. So by now somebody would have introduced what are the different industrial revolutions have happened and how they are actually progressed over a period of time. Okay, so now in case of any messages, maybe I would not able to see because I will be in the PowerPoint mode. So somebody can alert me, maybe organizers. Yeah,
Yes, sir. Sure, sir.
sure. Okay, I'm moving into the PowerPoint mode. Thank you. Yeah. So here a overview of the talk, though it may not be the sequence whatever I've written here, but this would like to, I mean, you'd be understanding at the end of this particular talk, like AI and its relevance, digitalization, data analytics, and Industry 4.0, and then CPS and the digital twin. Here, maybe I'm not sure if somebody has covered about digital twin. Uh, Dr. Guru, anybody covered it on digital twin?
So just basic what is mean by digital twin given by the Ravi sir, sir. Basic information.
Okay, fine. So, how the digital twin and the CPS are very similar to each other, but of course they have small difference. And robotics and the progress over period of time will be seen. AI, CPS, DT role and robotics also will be understanding by the end of this particular talk. So let us move on. So I hope we don't need any introduction to AI by now, because all of you have heard or worked or maybe applied, maybe written some papers, or maybe some projects are done, things like that. So if anybody needs introduction to AI, don't write. Do you need? Even if somebody one person asks for introduction, then we'll take up. Needs? No response. Okay. So I'm assuming that nobody need introduction to AI, but we will have some slides related to that, but not now. So if you see the robot, the historical timelines of robotics, of course, don't go by with this whatever picture that I have put. The robotics is not always humanoid. Robotics are like varieties of forms, and each country has their own definitions. Certain countries include even small automation also a robot. Some countries they exclude the automation part from the robotics boundaries. But anyway, that is not our intention right now, the motto to understand about the robotics, but how they are progressing over a period of time. I have given some reference here, but however, small timelines, if you see, actually it dates back 300 BC, but 300 BC to maybe 1500s, there are not much uh, progress on the robotic side, but there was some automation related to clock and mechanical birds in Egypt, maybe which are now we call part of, I mean, drones that we are birds, flying birds, I mean like robotic birds, but that were there during the Egypt time, but they are mechanical, not electronics or computing based what we have now and Greece. So these were there in Hero of Alexandria. So in 1495, Da Vinci sketched few of these humanoid robot concepts, okay, which were actually the maybe the early part of the robotics that we are talking about, but they were only on the books, not on the physical. Of course, maybe they would have done, but there is no evidence or any physical evidence of those developments. But at least people have uh, collected on the books or scripts that Da Vinci had sketched. So the first industrial revolution during that time, sorry. So please excuse me if I'm coughing in between. I may not able to restrict, but so industrial age, that is 1700 to 1800 time, you see, uh, lifelike automata like a flute player or a digesting duck. So these were there, I mean, built during that time, but it's not related to industries, but some kind of entertainment or some kind of maybe particularly entertainment, not anything different, right? So, but in the year of 1801, Joseph Jacquard invented punch card control looms, basically. So that way, this hand loom uh, were actually the you can say first computers in a way where the design of the whatever the cloth that is being loomed on the hand loom or the mechanical loom at that time, they were having some kind of punch cards which are programmable and which are precursor to programmable machines, which means not before the Babbage age actually. So that way, the first two computers are handlooms, we can say. But anyway, so 20th century birth of modern robotics with the term robot coined by Kopek in the play Rosam's Universal Robots. So in fact, now there is a company by name Universal Robots, a robot. So this happened in 1921. Of course, I don't think we need to go through all of these, but our interest is basically maybe from this where 21st century intelligent and autonomous systems are the main thing. Like in 2000s, sometime Romba, maybe it is I think 2004 or 2003, I believe. This vacuum cleaner was first developed, which is service robot kind of thing, which does autonomously to clean the floors. During that time, little later, surgical robots have come up, which named as a Da Vinci, and also some humanoid robot. This is actually in 1999, I believe. Japan, this company developed this humanoid, which is named as a Asimov. Then 2010, integration of AI, computer vision, machine learning enabled robots to navigate, recognize objects, and interact with humans. So this is actually the first development. So here you can see the importance of AI started where in line with the computer vision. So how these are helping robots? I mean, in fact, these robots are with AI and computer vision. These robots are given with extra sensors like vision sensors. They're like what human beings are having. And 2020's emergence of collaborative robots is called cobots in short form. Autonomous drones, warehouse robots, and Amazon's Kiva. So warehouse robots are basically they do a lot of activities. That I mean, I think I have one slide which details about it. And of course, self-driven cars are actually not in 2020s. It started much early, but they become famous 2020 onwards because of lot of companies entered into this domain. And of course, sometimes some bad incidents give big advertisement to those things, and that's how it becomes known. It become known to everyone, right? So these are in brief. So here, this the 21st century onwards, the whatever the development that maybe will again look back them. But however, let us move on this. So priority, we have to understand digitalization and digitization. Digitization is nothing but just mm, converting something, whatever in the physical form, into a digital form or a document form, or you can say signal form, by generating series of numbers that describe discrete set of its points and samples. So strictly speaking, digitizing simply means that converting or conversion of analog source material into numerical format, right? So that's what actually digitalization. However, digitalization is different. So here, even Wikipedia redirects into digitization when we call digitalization, because when I created this slide at the time. This digitalization was not actually properly defined. But later, this digitalization is, we see whatever process that manually being followed, exactly we cannot repeat, but e- exactly the end result we can achieve through some sequence of operations, or we can say in the latest lingo, pipelines. So sequence of pipelines, if you follow, you'll get the same end results. In simple term, maybe if some of you have ever booked your ticket by going to railway station, whatever the process that is followed, if you know, versus whatever process that being followed in IRCTC, how these are different or how these are effective. Uh, I mean, how these are particularly helping the human when compared to manual done and then digitalization activity. In fact, if you go little back in terms of time, so the booking of railway ticket was even bigger task. It is not just uh, maybe few minutes activity, but sometimes it was taking one day completely, because if you are booking some onward ticket, then you may have to wait confirmation from the other city from wherever you are booking onward ticket. So that is the difference. So similarly, any activity that is manufacturing process or any chemical process are involved in sequence of steps. So those sequence of steps, if human is being, human is operating that, how he operates, versus if robot is operating, how it operates. So here we assume lot of things when human is operating certain processes. So we assume that the visual feedback is, uh, without any consent, we assume that it exists. Similarly, some kind of consciousness, we assume that human will be having. So how do we bring the similar consciousness or similar understanding or similar feedback into the robot is what actually the core requirement. So these things are possible to achieve through AI. And in between the CPS, whatever we are calling, that is cyber physical system, uh, it's a basically scenario. It is not a technology as such, but compared to AI is a technology, but CPS is a way of doing it. Okay, so how these are different, that we'll see over a period of time in these slides. So before that, I would like to give some brief about the industrial revolutions that are happened from 1 to 4. I think many of the speakers would have spoken on this, but I briefly touch on this particular one. So first industrial revolution is based on water. Uh, Second industrial revolution is based on the electricity, and third industrial revolution is based on the kind of electronics, or you can say PLC in simple. That is a programmable logic controller was the distinguisher from the second industrial revolution, which actually made a lot of automation in the activities. The fourth industrial revolution, actually the one which currently going on, the the happening thing. So in this, yes, please. Anything? Somebody has any question? Yes.
The fourth industrial revolution is related to cyber physical systems. No, can we say cobos also are included in that?
Pardon?
Fourth. Fourth
fourth
industrial
industrial
revolution is
revolution is
related to cyber physical systems. No, can we include cobots also into that?
yeah, it's a basically, see, cyber physical system here. The assumption is the cyber physical. This terminology we'll talk about, and then if you see here, robo also there,
Hmm.
right? You see that there is a robo also, right?
Hmm.
So how these are relevant, that we'll see. Okay, so yeah, your point is right. Hobos are part of this Industrial Revolution 4. Okay, see, where it took from, I mean, when it actually started 2011, the cobots were just getting shaped actually at that time. So cyber physical system was main focus at that time because of the connectivity, and as well as, in simple term, if you see, it is something related to hardware in the loop. If electronics people are here in this, so it is
Yes, sir.
very similar to hardware in the loop concept, but little advanced. Okay. And here, the degree of complexity scale, if you see, industry 4, from industry 1 to industry 4, the complexity is vertically, exponentially increasing, right? So this is the, in simple, industrial revolutions. So here, this slide should have been little later, but however, I wanted to touch immediately after this industry 4.0. So here, when you see here, I mean, if you put operator at the each level, what were they doing at that time? If you see in that perspective, where robots also come into picture. So here, for your point, here, human CPS, that is in other way, it's a cobot. Human CPS is nothing but human, and then the cyber physical system. So cyber physical systems here are replaced. I mean, robots are replaced with the cyber physical system name, but in a way, it is a robotic system only. Okay. So here, let us go with the operator 1.0, 2.0, and 3.0, 4.0. Here, there is only one equipment on which multiple operators are working. So some may be supervising, some may be actually working, some may be helping. Here only though two operators are being shown, but you would have seen there could be multiple people who will be operating on the same, maybe with the different roles, right? So where the mechanical tools, manually operated machine tools. So here, this is the scenario where manual and dexterous work, which means mechanical tools and manually operated machine tools. So which was happened like 1700 to at least 1960. So till this, in other way, till this PLCs are invented, till then the mechanical operators were there. In fact, in a way, it covered two industrial revolutions, right? Industry 1.0, Industry 2.0 covered within this. That's what up to this. This entire zone is with the operator 1. So, right? So if you see operator 2, assisted work by CAX tools, numerically controlled operating systems, and enterprise information systems. So all these are they are assisting the operator 2. So where, in addition to the automation that entire industries is automated, so along with that, there is certain informations and certain computer-aided design, computer-aided manufacturing, computer-aided process planning, computer-aided many other things. So such kind of tools are actually helping the operator too, and then you have numerically controlled operating systems, and then you have enterprise information system. So enterprise information system is end to end, like from raw material to actually selling something out after producing it. So everything will be available on the enterprise information system. However, here the operator will be knowing what is the amount of production to be done on that particular shift or that particular day, and then what are the designs that need to be produced. All that information will be available because of the CAX tools. So all that process plan also will be given to him dynamically. So you don't have to like carry any paper. Everything will be available on the system on even his computer. So that's what the case. It ran only for 10 years. That's what is being shown here. But later, the industrial robots introduced where cooperative work with robots and machine tools or computer tools are done. So which ran for 30 years. However, the cooperative work is different than collaborative work. Please understand here, robot is cooperating with the operator, which means based on his instructions, it may be doing something, or based on his program, whatever he does on the particular robot, that robot may be doing certain things. It's not pre-programmed. It's not autonomous on its own. It will be programmed for maybe certain conditions. Based on certain conditions, it will be working. So here, however, this was moving towards human robot collaboration. So which is not yet collaboration, it is only cooperation. So that is ran up to 2000. However, this it's not just immediately jumped into cyber physical system, but there was a lot of transformations happened during this 2002, 2010, 2011. Actually, Industry 4.0 started. So which means the operator 4 has started much earlier than Industry 4.0, right? So if you see, this is starting point of the Industry 4.0, whereas the operator 4 started little earlier. So here if you see, work aided by machines. So which means human cyber physical systems. So both, which means cyber physical system will have certain definition later in the slides itself, but we'll see that. Any questions till now? Okay, I assume there are no questions. So the trends, if you see, maybe you know by now how the Industry 4.0 digital twin cyber physical systems are actually ruling the industry in terms of manufacturing solutions or enterprise digital enterprise solutions, or maybe Internet of Things, and then process industries or steel industry or power industry. Like there is no vertical or industry which is not touched by Industry 4.0, or part of that industry is touched by Industry 4.0. So most of them are in fact all of them are touched by this, but however may not be implemented in certain countries, or may not be maybe seen light of it in certain countries, but some other countries have progressed in those domains also. So that's what actually happening. So this is ArcelorMittal. If you see how they are seeing Industry 4.0 is a breakthrough for, is known for breakthroughs in nanotechnology, quantum computing, biotechnology, the Internet of Things, fifth generation of wireless technologies, 3D printing, additive manufacturing, and fully autonomous vehicles. So here, fully autonomous vehicles and fully autonomous labs kind of thing also we have to think of. So that we'll see. So how IoT solutions alleviate the pain point of the industry. So here, So for any industry to progress in terms of AI or something, it is important to have the data or observations that are, like for example, when certain action is taken, what is the response? Unless you measure the action that you have given to that particular system, we will not have any way of measuring their effectiveness or their correctness. So that is what actually important here, and that's where the IoT or Internet of Things will work. So basically, Internet of Things are these connecting the sensors in a way. So that's what actually will collect the lot of data about the system, which helps us in terms of monitoring and things like that. So we'll see certain examples, not examples in fact, but some cases here. We'll see that. So maybe we'll come back to this, not required. So who gains from digital transformation in Industry 4.0 is basically the leader, the manager, supervisor, and operator. All of them will be gaining this in terms of uh, whatever, I mean, when digitalization is done. So here, all the manual works will be removed uh, to automation, and then automation things, which means the manually you don't have to work, but you may have to mentally work and then get the things done. Mentally, in the sense, the intellectual of the people, the knowledge of the people on particular technologies need to be improvised so that they are empowered to do certain things, maybe at the leadership level or maybe at the shop floor level. So these are required. So this is what the digital transformation brings in the industry. So if you see real world, of course, why this slide is there, we'll know once we go forward. So in the real world, systems are inherently non-linear. So in terms of dynamics and unstructured uncertainties. So uncertainties are also further unstructured. So it is not structured uncertainties. So nonlinear interaction between subsystems adds up to the dimension of the problem, which means uh, subsystems are also nonlinear and their interaction further becomes complicated. And spatiotemporal dependency on self and influence neighborhood subsystems. So this is the three important factors the any real world system will have, and then actually that's what actually drives a lot of complexity in the system. So why this is relevant here, we'll see this. So here, when such kind of complexity you want model, it is not just building a neural network model where few inputs or few outputs are there, and then maybe predict whatever output and then close the chapter. No, it is not like that. So we need to have it is not just map meeting the point to point prediction, but it is meeting the behavior, which means you have to capture the uh, system behavior into the model. So which is not just a neural network approach where it is mostly statistical, I mean not statistical, static mapping, which means there is certain inputs which are actually producing certain output. There is no time dependency. So this instance input is given, output is given. So like that we have map. So which is static behavior in the data. So if you start, whereas real world systems are not static. That's what in the previous slide I was talking about. They are inherently non-linear, right? So how do we actually capture that is what actually the modeling is important, and then that's when the digital twin comes into picture, where you can bring a lot of what you can say richness in the model, or you can say fidelity in the model, which will be helpful in terms of uh, actually modeling uh, sorry, modeling more scenarios uh, far from the real time. I mean, much ahead of the real time, and then identify more suitable scenario and implement in real time. So, which means, suppose if you want to implement in real time certain changes, so you may have to verify thousands of different scenarios and come up with one particular best scenario and implement into this. So, which means this should be much faster than the real time. So that's what is possible through digital twin, of course, with the highest computing power that is available in current generation. Right. So here various systems are given, of course, smart grid, autonomous automobile system, medical monitoring, process control system, distributed robotics, and the automatic pilot avionics also into this. So that is in simple. So what is cyber physical system is a connected entity of intangible here algorithms, software or process, and tangible, which means physical system, which is equipment or production assets in terms of is termed as a cyber physical system, which has key role in the industry 4.0, a fourth industrial revolution. So cyber physical system is a mechanism controlled or monitored by computer-based algorithms. For example, so cyber physical system includes these. So this is what actually cyber physical system. It is not a technology or algorithm, but it is a way of implementing certain things. So that's what I was mentioning in the previous slides. So in simple, computation, communication, and control put together, the information is generated or used both. I mean, it generates information or it uses this information to control the cyber physical system or system, physical system per se, right? So I suddenly jumped into here. There is a reason why we jumped here. AML. So I in the first slide I said AML don't need any uh, description or introduction, but it does need, because we need to know where we are progressing. So here, under a general in artificial intelligence, okay, there are many sub domains or sub areas of things. So which we call machine learning is one of the AI, under AI umbrella, where further if you, narrow down, artificial neural networks is the next layer, and then within the artificial neural network we have deep learning, and then deep learning also has certain applications called Gen AI or generative AI we call. Of course, responsible AI is not the technology or algorithm, but it is maybe the ethical point of view. How do we actually use the AI is what also important aspect. So we cannot have a AI just like that in any of the system. So there is some ethics need to be followed, or some responsibility need to be followed in the AI. Like currently, if you see, agentic AI is going on. So agentic AI is nothing but uh, using AI system to actually perform certain things autonomously. So here, if these things, if agentic AI is actually part of robotics, so that will be helping robots to do things autonomously. So that's where actually the importance of AI comes into picture, how it is actually the improving the role of robots in the day-to-day life of human being. So further, if you see, neuromorphic computing is the other area. Of course, it's not part of the AML, but neuromorphic computing is the one which actually improves how robots will be analyzing the scenarios, or maybe interacting with the human being, or maybe sensing the environment and reacting to the environment through that. So, neuromorphic computing will mimic our brain in a way to help robots to perform like human being, and that's where actually most of the humanoids or humanoid robots are I mean development is targeted with the neuromorphic computing. So till now, any questions? Okay, let's move on. So these techno, I mean, this I don't have to list down all these. These are known to you people already. This also I don't. But a generic framework, if you see how the data is transformed into model, it's a very generic framework, and it is algorithm independent. But right now, it appears only as a static modeling or relationship mapping. But there is much more than this, which is not part of this particular talk. But anyway, so here business understanding is very important to actually understand the data, and then business understanding and understanding data will exchange each other, and finally you come up with the conclusion that okay, a list of data or you can say list of variables that need to be added in the data, which you prepare and then go for modeling. Again, modeling and data preparation will be interactive, where certain data may have to be transformed into a certain domain to have a better performance in the modeling. And then once the model is finalized, you will be evaluating its performance and then understand the business things. Once this is mapping or matching the requirement, then you deploy. So this is the cycle that actually goes in the model development and deployment. So here, whenever certain things are required on the robotic side, so these AI models will be developed to meet those business understanding. So here, business understanding is nothing but a problem stated. So the problem stated by that particular, I mean, whatever the situation, and then what kind of data is needed. For example, let us say there is a robot which is actually picking up certain object from conveyor belt, which is actually moving with a certain speed. Can you mute if you don't mind? Somebody has.
Yes,
Can you
sir, I
mute
have removed
your?
him. No problem. I have removed him.
Okay, okay. So here, these things, so these requirements will be actually converted into data requirement, and then I mean business requirement into data requirement, and then model will be developed and then deployed into that. So yeah, what I was talking is if you want pickup from the conveyor, so with certain speed it is moving, then the robot has to be, I mean, has to move to that point and pick up that particular object, which means here there are few things involved. There should be synchronization between the conveyor belt speed and robot movement to that particular position, and also the object recognition need to be done prior to that. So object recognition, its location at when it is actually recognized, and then the amount of time that takes which to reach the robotic position, so that need to be calculated, and then you have to instruct to the robot. So here this problem statement, if you want to convert into the robot capability, then what kind of information that you need? You may have to capture the image, process it, and then find its location and then send it to robot, so which the robot will have knowledge about the position uh, of the object when it is being recognized, and then position of the object when it is being to be picked up. So this information need to be there, but everything, all these activities should be part of the robot, so which will be doing it autonomously. So that's the importance of AI here in this particular problem statement, right? So everyone maybe by now would get, okay, AI was there for maybe last 70 years or maybe 60 years, right? 1949 or sometime back, neuro model or artificial intelligence name was coined. So from that point onwards, we have artificial intelligence. So, but why it has gained so much importance now? There are actually, if you dig through the history or dig to the progress, there are three fundamental things that actually uh, paradigm shift has happened completely in terms of computing, in terms of communication, in terms of data storage or storage capacity, you can say. So these three fundamental parameters actually change the entire scenario, right? So let us see few of these things. So any one of you recognizes this? What is it? What is it? I'm surprised when 200, more than 200 faculty members, not students, are there and nobody responding. Till now, only one person has responded. Okay, I'm happy to see that at least. But see,
Sir, sorry, sir, interrupt you. Not like that, sir.
uh,
We are
see,
interesting
always,
too.
yeah. See, always one or two can respond. I mean, uh, so
Okay,
maybe this kind of scenario will come into picture. Is what you want to develop.
okay, sir.
Okay, so I understand. So because the time that we have chosen is such a way that all of you may be at home, and then there will be a lot of background noise which you don't want to project it. This is what I am assuming. I'm proceeding, so that I am also happy to see. Okay, this is ENIAC. I mean, the first computer you can say, right? So, which is like almost a complete warehouse kind of thing, a single computer. Okay, do you understand that? So it's a single computer. Whereas here, if you see, there are like form of high performing computers racked at various levels, and then maybe you would have heard certain uh, these HPCs, I mean high performing computing farms, or you can say, no, people call simply data centers. Actually, it is maybe sometimes it's a misnomer. It's not just data center; it is basically high computing devices put together. So they run. I mean, they need maybe 1 gigawatt of power. So that is the actually power hungriness of these computers, which means you can assume. Suppose if your computer is actually taking 60 watts, and then these farms are actually taking 1 gigawatt, just you can imagine how much the power of computing they are holding. So the power of computing that much is available now at your fingertips. As long, I mean, once you have access to those kind of computers, so you can do many things. So that's the paradigm shift in the computing, right? So similarly, if you see memory or storage capacity in a way, the first one shows 1956. They are actually pushing a big, I mean, box, maybe 1.5 meter by 1.5 meter by 1.5 meter approximately, which is actually 5 MB hard disk. Okay, so it's a very funny, right? But now, if you see into 2020, okay, this is a little aged photograph now. I think 2025, we have already crossed 2 TB memory card or micro SD cards. So there is, if you actually compute the memory density, it is almost 10 to the power of 12 times. 10 to the power of 12 times, which means billions, trillions, yeah, trillion times, right? Trillion times higher density, which means at one dot we are able to store one digit in 1956. Now we are able to store 10 to the power of 12 digits. That is the capacity. Similarly, on the communication side, you see, now we are talking about 5G, 6G kind of thing, right? So 1G, 2G, 3G, 4G, 5G. This is, if you see, the amount of the data transfer capability per second has increased drastically from just a few bytes to 1 gigab. I mean, yeah, few bits to 1 gigabit capacity. So that is the paradigm shift in the communication technology. So all these together, three concepts. Of course, again, storage has come. This we would have seen various storage things that is not required. So all these three fundamental technology development put together, there is actually now AI has become a domestic tool for most of the activities. So that's how the AI become possible or feasible in current scenario because of this computing, storage, and communication. Right. So here a simple use case I have given. Of course, here why industry needs our industry data is so complicated because of a variety of frequency or messy data or complex data relationship, massive. And also, yeah, this varied frequency is one, like you have multiple sensors. Each sensor may be having different frequency at which they are capturing the data, but at the end you should able to normalize to one particular time frequency, fuse all the data appropriately, and then use them for modeling purpose or understanding the system. And you have variety of source types, like for example it may be numerical data, or it may be vibrations data, or it may be noise data, or it may be visual data. So all these data varieties are available to be used in the industry. So again, certain times so these are messy because sometimes some data may be missing altogether, some data may be actually wrongly tagged, and things like that. Of course, these are solvable problems. Of course, certain times these are also not solvable, but however, we assume certain things are solvable and use it. And then these relationships are very complex in nature, which is very difficult to actually put in terms of just relationship databases. And of course different sizes, as I mentioned, there will be like certain uh, sensors maybe like capturing data at 1 hertz, certain sensors capturing the data at 20k hertz. So that is the range in which the data will be captured. So that is the different sizes we'll have. And then of course massive values. That is the reason why industrial data sets are complicated. So if you see simple process, that is maybe steel making process, to understand physically how these are actually done, there are multiple steps involved to produce steel, maybe sheet metal like this. So you give raw material here in the blast furnace and then move into different steps. Maybe here some scrap also. Instead of raw material, you use scrap also, and then produce steel making in a electrical arc furnace. Then you merge them here, produce maybe in this particular case, I mean continuous casting. So in the continuous casting, this will be put into ladle, tundish, and then mold actually producing the sheets. The sheets will be cut at appropriate lengths and then moved into further processing. Maybe you enlarge it, or maybe change thickness from the requirement to requirement. So this will be moving. So again, so these are picked up so into pickling line, which means basically there will be processing, some kind of post processing will be done to go into heat treatment or things, so that the material that is produced are having uh, appropriate properties, because based on the requirement these processes will be changed, and then those will be acquiring those properties. So this is actually the physical environment. Suppose if you convert this into a digital environment. So here CPS integration into Industry 4.0, if you see, so each one of these you have cyber physical model of the system. So this is blast furnace of cyber physical model, and this is another BOF cyber physical model, and then this is continuous casting cyber physical model. You have a roller mechanism, roll, that is cyber physical model for this, and then here you have changing the thickness of the sheets. Also, this is also put into cyber physical model, and then here you see they will be exchanging the information from one to other, so that these cyber physical models are not not isolated. They are connected. They are connected to each other. So which means in real time they can exchange and then do certain simulations across, and then they'll know, okay, which if there is certain kind of process parameter need to be changed,
Sir,
that will be
excuse me,
suggested.
sir.
Yes,
Sir,
please. Yes, please.
sir, excuse me, sir. What is
Yes.
the difference between the CPS and IoT, sir? Both
Yeah.
are similar. Huh?
Not similar. IoT is basically it's a you are collecting data through placing some sensors. IoT, Internet of Things, right? Internet of Things is basically collecting data, whereas cyber physical system is you have some replica of the physical system in the computer domain or cyber domain, which will be interacting each other. Cyber system and physical system will be interacting to each other to actually evaluate certain scenarios. That's why it's called cyber physical system. Whereas IoT devices just collect data. If you have a device, computing device attached to the IoT, then it becomes edge computing. So they are entirely different. I mean, you cannot match or you cannot compare IoT and cyber physical system. Right? Hope it is clear. So here, these things will be keep on exchanging information and optimizing overall process, and then properties of the end product. That is important things. And at the same time, along with this, how this supply chain also optimized is what the next level of things that is happening already. So in the certain areas, here I'm talking about the steel industry, but every industry has certain scenarios already happening. Okay, right. So here now the data, whatever somebody asked, I did not see who is asking name, I don't know, but however, whatever he is asking in the similar lines, that IoT devices collect data, right? So when you have data, each data will tell certain story. This story, we can say telltale signal. I mean, the data that is captured through various measurements or IoT devices tells some data, and then we call that as a telltale signal of the behavior of the system that is being monitored through this IoT, and then converting the data captured into a representative model using data driven. So, what we were talking about, generic model development framework. So, we'll embed the knowledge into the model, so which can be used. So, this is a very generic sheer model, whatever data driven system. It's not just mapping the static behavior, but dynamic behavior also we should consider here. So, for example, from the model, it is possible to see through the time period. So, if you want to see through the time period, the model has to be dynamic. It's not just static model. So, which means inputs to output mapping. It's not just input to output mapping, but the time dependency also brings into the model. So, before actual plant reaches there. So, that's what actually here, whatever we are talking about, how these are actually capturing, they are done in the cyber domain. Of course, we should have actually labeled this as a digital twin of each one of these, not the cyber physical system, because cyber physical system enforces that the physical system and the cyber system are in loop to each other continuously. So, which is in this particular case, if you want to generate scenario, like for example, this scenario that whatever we are talking about, the third point, we want to do that, then these systems we should have digital twins of those particular equipment or assets. All these should be, I mean, instead of cyber physical system, should be digital twins of those systems, and then where you can see through time and then get the various scenarios explored and then finalize on one particular one. So also many control strategies are possible to implement first on the model, and then if satisfied then you implement into the real physical system, through which lot of time and energy is possible to save and improve the outcome from the real plant. So improve the outcome from the real plant is what, so that you don't have to experiment on the real plant, which sometimes may go into catastrophe if you directly implement certain scenarios onto the real plant, so real life plant. So it is always safer if we actually implement on the digital twins first and then explore, satisfy, then you implement onto the real system. The same thing happens in the robotics also. These scenarios can be explored on the digital domain first, and then once satisfied, then implement onto the real. So this is what happens in the most of the industries. Uh, Before they actually deploy these robots, all the scenarios will be explored on the digital domain first, and then get on to the real. So that's where the digital twin, cyber physical systems, AI comes into handy. So here I'm actually going little background also, so that you get some idea. So let me see what is time. We are near to. So we'll speed up little fast here in this case. So data analytics is an analysis of data, and not only that, inspecting, cleansing, transforming, and modeling, all put together we call data analytics. So here we have, um, so let it go on. So we have different scenarios here. So we don't get into the details of this, but of course, transforming the data, raw data into information. I mean, information and then intelligence is the complete flow of the data analytics. So here we have multiple scenarios to be explored, or maturity level of the data analytics. So here there are two maturity models that we have. Of course, there are many others, but generally I harp on these two maturity models. These are because number one, it is by Gartner. So here, descriptive analytics to prescriptive analytics, four different analytics types are there, and then the value that they add goes vertically from first one to fourth one, but also difficulty also increases by the time from the 1 to 4. So descriptive analytics, diagnostics analytics, predictive analytics, and prescriptive analytics. So here if you see, first one sees what happened, which means as it is, they see. And then diagnostics is post-mortem kind of thing. Why did it happen is what it does. And then predictive analytics is what a kind of preventive approach it gives, so that it will, what will happen we can see in beforehand and then take appropriate action. Now prescriptive analytics is what is basically how we can make it happen is the prescriptive analytics. So here the information is converted to insight and then optimization level. So that's what actually the maturity model of the Gartner. This way I label as a maturity model 1. And similarly, we have maturity model 2, where the automation, so how the automation is, or how autonomous it becomes, any system. Here, if you actually imply to robotics, here descriptive analytics is, I mean, you can say previous industrial robots where there is a lot of human input, and then as it progresses, diagnostics, there is a balanced human input and data analytics, of course, but the decision is still by human, action also still by human. Predictive analytics, if you see, the human input is further reduced, but still decision is by human. Similarly, prescriptive analytics, if you see, is decision support is still by the data, decision is made by human, but and the second prong, if you see, decision is also automated, but action is still, I mean, can be automated further, right? So this is what actually maturity model 2 on the data analytics. So here there is a lot of information that you can derive and then imply in terms of robotics. So how the robotics have evolved can be actually seen in this particular thing. If you can imply that, right? So this, so we don't have to run. So here the digital twin is the ultra realistic geometry detail, including manufacturing and anomalies and material details, including statistical microstructure level, specific to particular make and then specific to particular item itself. So it is very, I mean, we can say the description are very generic, but in simple terms, if you see, digital twin is represented as a single entity, but it may be consisted of several components that are intimately linked, such as thermal heat transfer models and dynamic models and stress analysis model and fatigue. Because you see, if any mechanical system is working, all these thermal heat, thermal model will be there, dynamic model also will be there, stress analysis, all these cannot be done in a single model. So, but you can combine all these information together and then build a digital twin which will be responsive, right? So that is in simple digital twin, but yeah, this we don't need right now. This also we don't need right now. Yeah, here digital and physical space, if you see, maybe we'll come back to this later if time permits, because yeah, this is what is actually important first. We'll come back to that. So digital twin,
Yes, sir.
yes, please.
Sir, we have last 10 minutes, sir. Can you please speed up?
Yeah,
Sir?
yeah, yeah, yeah.
Please.
I'm,
Thank
I
you, sir.
mean, I'm tracking that. I'm tracking that.
Yes, sir. Thank you.
Yeah. So digital twin actually in 2003 started, and then now whatever status you see, 2018, of course, 2025 we are. So, but digital twins are there in the most of the areas, along with, I mean, on par with this cyber physical system, because they share a lot of similarities, right? The origin of cyber physical system and digital twin towards smart manufacturing, if you see, these are traditional IT, how it was working, and then cloud computing, IoT, big data analytics put together here. And then there are two approaches. One is cyber physical system approach, another is the digital twin approach took, where here this is tightly combined, this is loosely combined, right? So that is the difference in terms of cyber physical system and the digital twin. So where both are having physical and cyber, here we call digital twin in virtual and physical, whereas in the CPS we call cyber and physical. Here we have, in the physical system we have sensors, and in cyber we have controls where you can have all the scenarios and then exchange information. Similarly, here in the physical system, sensors will collect the data and then pass on to the model. Model will verify all the scenarios and give the feedback to the physical system. That's how this moves. And then now they are merging to become part of smart manufacturing, that is cyber physical system data, digital twins. And then that's what actually I was talking in the previous cases slides, right? So mapping between physical and cyber digital worlds. So here, so this is what actually integration of cyber physical system and the digital twins. So here you can see this particular one. If you see, uh, this is physical world and this is digital world, but actually, if you see this put together, it's a cyber physical system, right? So here, these robots are actually verified for various rules to be followed, whether materials are actually working for the given scenarios properly, whether there is any violation of the rule. All that can be verified or checked in the digital twin domain or digital domain, and then give feedback to the physical domain. So where this physical system will work. So in the cyber physical system approach. So this is what this exchange of information and data, feedback and data will continue, and then we have data analysis and all these data decision making applications together, right? So this is what actually cyber physical system and the integration of digital twins. So these are like a hierarchy of digital twins and cyber physical systems together, and then we have, so actually further explanation of the previous slides only in detail. Of course, here also very similar, like how do we split, how the data sensors and what kind of sensors we are actually having on the physical system, and what kind of models are having in the digital domain are actually given, and then how do we integrate them as a single virtual world. So these are all there. Here, these are all not required because it's not digital twin concept that we are talking about. But however, I would like to just share there are 5-dimensional digital twin concept where physical entity, virtual entity, services, data, digital twin data, and connection. There are 5 dimensions here. So how these 5 dimensions are put together, connected, like this is services and physical entity, services and virtual entity, physical entity and services, virtual entity are connected with this, and then like this data and digital twin data is collected data from all these scenarios put together here. So these are all actually moving towards that. So that's how the cyber physical system will be using the information from the digital twin, right? So all these are there. So this is one of the use case of the manufacturing, where Internet of Things in the manufacturing also talked about, but it's not just Internet of Things, but the entire system, smart system or cyber physical system put together. So this is, I don't know, so yeah, background of these are all there. These are there. Yeah, building blocks, digital twins. Yeah, trends. Actually, there are big trends. Maybe if time permits, if 5 minutes, if it can be further. I think we have 10 more minutes, of course. So let us touch upon these autonomous mobile robots, where these are all like, if you go through these, like what kind of sensors are required to actually navigate in a known environment and in the unknown environment. If you see on roads, it is unknown environment, but inside it is a known environment, which means you can map and then more or less it will continue the same. So similarly here, this is a maybe AGVs, the autonomous guided vehicle, in other way now we can call. So all these are kind of mobile robots, autonomous mobile robots, AMRs. So similarly, hyper intelligent robots, where they will actually assist you in terms of various ways. Like in this case, C's office assistant, which is actually who is taking help from the humanoid robot in various cases. So similarly, these are humanoid robots for services, right? So here, if you see, sees CBI person who is taking help from the humanoid robot, or you can say virtual robot, who is not physically available but virtual domain. So, but she will be interacting with her, and then get the informations clarified, because humanly it is very difficult to search all the data that is available and then come up with some certain things. So this, I think, this robot Sophia, you would have seen what she was talking about, and then how intelligently she was replying, right? She's also again an office assistant here. Humanoid and social robots. Third thing. Fourth thing is soft robots, where pick and place is what the main activity. Of course, if you want to have a touch and feel of the robots, maybe shaking hand kind of thing, are also possible through this, is what actually demonstrated here. And they are flexible in terms of navigating any unknown, or you can say unstructured domain passages. So these are all different ways of these grippers. You have a robotic exoskeleton, where you can wear that and walk. If you, I mean, if the body is paralyzed, I mean, somebody, a paralyzed body can use these robots and then walk. So you don't have to depend on somebody. So here example is AI-powered exo suit for spinal injury recovery. So this person injured spinal. So to recover from that, exoskeleton robot is used. Of course, these can be used as a, military equipment also. Like if you have seen Avatar 1, so in that, whatever exoskeleton, in fact, the person will be sitting inside the robot and then navigating through that, right? So those kind of exoskeletons. So here, similar to that, whatever I was telling, Avatar 1, so these are smaller one, which will be helping the human to pick up heavy loads. So here it will be assisting the robot, collaborative robots, where it will be assisting the operator to actually maybe cut the something. Here she is doing some operation. So here this particular robot is collaboratively assisting her. The sixth one is again, yeah, I don't have in this particular case. Okay, we can see that here. What is the difference between cobots and conventional robots is what actually talked about, where cobots are actually not like programmed per se, but whereas in industrial conventional robots are programmed for certain actions. Other than those actions, it cannot do. Of course, in the cobots also certain actions only will be there, but now they have capability to learn and then do that, do those activity or repeat those activity by actually watching once, not even twice, just once. If watch, they can repeat it. So similarly, swarm robots, particularly you can say drones, how they actually navigate or swarm and then do certain activities. And then also space robotics, where this is space, you can say uh, Astro B. This is called Astro B. It's a robot actually, and then it works on the microgravity uh, domains also. Of course, this is a arm of maybe all the robotic arm. So where robots will be the war people. So here robotics as a service is ROS. So where the Amazon kind of data warehouses are being maintained or uh, maintained by these autonomous robots without human intervention. In fact, these days, some companies are not using lights because everything is being operated by robots, and then if they are infrared capability, they can do without any lights. So there is a lot of power saving. That's what they are claiming. So we have to see that. So again, ROS for public services. So these are deployed or hired for given activity, like the way you hire AC from particular occasions, like that. These robots are hired for maybe hourly or day wise and things like that. That is what going to happen shortly. So robotics, cyber physical security in assets monitoring. So here you would have heard Dubai. We have already RoboCop working 24/7, monitoring certain assets, particularly airports. Right? You have advanced surgical robots now, which will be. I mean, somebody can operate from remote, which are like work as a this as a work as a assistive robots or slave robots. Otherwise, they can also do on their own autonomously. That is also possible. So that is what actually the current trend. So future trends, if you see, physical AI, that is robots with embedded intelligence for real world decision making, is the trend going to be there. And soft robots, which we have already spoken a little bit about it, which are going to be there. Swarm robots also will be there. And then human robot teaming. So where you'll have there will be some composition of humans, some composition of robots put together, work in hospitals, homes, and factories. So robotics is no longer just about automation, but it is about intelligence, adaptability, and interaction. So that is what. Thank you very much.
Sir, so next generation war is robotic war, sir. Then
Pardon?
next generation war will be robotic war, huh?
Let us not talk about war. Let us talk about progress. That war will be there if a robot is there or human is there. War will be there. We cannot avoid certain wars. But how we can use the robots for betterment is what we have to actually focus. Of course, if people are saying if wars going to be there, those will be through robots only. But still, not. I mean, not all countries have reached that level. But certain countries are already acquired robots for war.
What are those countries, sir?
China is one, of course. US is another, and maybe USSR also maybe there. There is Russia. So any other
Participants,
questions?
read out, sir. Maybe it is a high time,
Yeah.
sir. There may be no doubts, it seems.
So all are exhausted, exiting.
Exhausted. Yes, sir.
I
But actually, you have taken a lot of pain, sir. Even though if you are not feeling well, you have delivered the session very good, sir. The slides
Thank
preparation
you
was
very
very,
much.
very attractive and good, sir.
Thank you very much. Thank you very
Right.
much.
Right. Sir, any feedback from the participants, sir? One or two lines about, sir.
Yeah, if somebody talks,
Yeah, it
if
will be good,
something
sir.
need to be
I hope Kalraja, sir.
added that, yeah, I'll maybe next time I'll add that.
Exactly.
Yeah. I hope,
We
I
have
mean,
active
at least
participants, sir.
50% people have heard what I was talking. I'll be happy. Yeah, some thumbs ups are coming.
Yeah, yes.
So hope
Reactions
so.
are coming. We are happy.
Thank you very much. Yeah,
Thank you, sir. Thank you so much, participants. Thank you.
thank you very
Sir,
much.
with your permission, shall we proceed for a vote of thanks, sir?
Yeah, please proceed.
Sir, on behalf of ATAL Online FTP, Robotics for Industry 4.0, I sincerely thanks Dr. Krishnay sir for an excellent talk on role of AI and cyber physical systems in robotics. Sir, your insights into AI integration and cyber physical design in robotic system were highly informative and inspiring. So thank you for sharing your expertise with us, sir, and making this session a grand success. I would also like to thank ATAL, the organizing team, me and Dr. Guru Mahesh sir, and all of today's session moderator, Dr. Vamsi sir. And last but not least, the all participants, we'd like to thank you very much, sir.
Sure.
Good night, sir.
I thank all the organizers and Atal and then participants for patiently hearing. And then, of course, I feel, I mean, there are no questions, but anyway,
Sir, we will be sharing your data, sir, maybe mail ID. So if any participant is having any doubts, they may
if
contact
somebody has any questions, they can contact me. Yeah.
Thank you
very
very
much. Thank you. Thank you. Thank you.
Thank you, sir. You can leave, sir. Sir, for participants, I have shared the link in WhatsApp also. Sir, PPTs, we would like to ask consent from the speaker, sir. Maybe they may not give, it seems, because all it is their own property. But we will definitely ask, as Rajashmi madam has shared me, I have shared you the data. Sir, my request is please don't post the attendance number, sir. It is not required, sir. Anyway, at the last, we are giving you the attendance link and all. Thank you. Thank you, sir.
Okay, sir. Thank you, sir.
Sir, if any suggestions from you, you please let me know. And tomorrow we have a very good speaker from IIT Tirupati. He is heading the mechanical department, Dr. Mamila Ravishankar, sir. And he is having a project proposals of 200 crores, sir. Maybe he will give definitely a good presentation for you. Sir, if there are no doubts, we will wind up the session, sir.